Okay. Recording video, audio, TBD.
Now recording.
Okay. I'm hoping you're going to give a recap of why Fermat's little theorem is true in the first place, because I don't even remember the proof.
Yes, I will be.
Sweet.
It's maybe a unconventional proof, but
That's fun.
like maybe not the one that a student usually learns.
Okay.
Because I don't really remember that one, and I don't think it's most relevant to this talk anyway.
Okay.
All right.
Welcome, welcome.
Hello. All right. Let's see. How do I share your screen? Let's see. Let's do the.
All good. No worries. No need to talk or participate.
Okay. So this should be sharing now?
Yep.
Okay. And feel free to like pause me at any moment and slow down or take a
I'm going to
tangent or
need you to
whatever.
not raise the bar this much on slide prettiness, because this is you're going to make me feel bad.
Oh, I don't mean I.
Also,
One
what
of the
language is
nice
that?
things about the system that I've built is that it makes it quite fast to make slides in the
That's
style.
good. That's beautiful.
Don't worry, my slides will make you feel better.
Okay, good.
All right. So this is about Fermat's little theorem with polynomials.
Sweet.
First, we should just talk about Fermat's little theorem normally. So, is this showing?
Yep, I can
Yes.
see that. Is that
Let me
German
hide
or
that.
Dutch?
Dutch.
Dutch. Okay.
So when p is prime, this is just in the integers.
Uh-huh.
If p is prime, then a to the p is congruent to a mod p for any a. And taking this out of modular arithmetic, what we're really saying is a to the p equals a plus some multiple of p. So for an example of this, 2 to the 5, which is 32, is 2 plus a multiple of 5. Another example, 4 cubed is 4 plus a multiple of 3. So this will hold for any integer and a prime. And we really just want to look at the case where a is not a multiple of p. This is really the interesting case, because
If it's
if
a
a
multiple of
is
p,
a
you just
multiple
get
of p,
0 mod p.
this is a multiple of p, this
Right.
is a multiple of p, so it's trivial that this is also a multiple of p.
Mm-hmm.
We really just care that it's not. So since a divides both of these, it must also divide the other term, but it can't divide p, so it must divide m. So we can divide out a of all of these. So that gives us a to the p minus 1, 1, and then some n. So this is like an equivalent statement of Fermat's little theorem, if we ignore that simple case. And this is actually, I think it's more interesting. It says that everything returns to 1 instead of itself. So any number will give us the multiplicative identity after p minus 1 exponents. An example of this, 2 to the 6 is 1 mod 7. And so kind of these a's make a p minus 1 cycle. So it's actually a little stronger than just when we raise them to the p minus 1 power. To illustrate this, we'll work in mod 7. So starting with 1, we'll have this arrow represent multiplication by 3. So we get 3. And then 9. But since we're in mod 7, that reduces to 2 since we subtract 7. So then multiplying again, we get 6. And then 6 times 3 is 18, but that's just equal to 4. And then 5. And then back to 1. So there is this 6 cycle of multiplication by 3 that hits every number, mod 7, except for 7 itself.
Is this the same thing as a magic cycle?
I don't know what a magic cycle is.
I could be drawing a connection where there isn't one. I'll look it up and update in the chat, I guess.
Okay. I can't see the chat.
After the call,
Maybe I should. Oh, okay, I see. That makes sense. Okay, so with this cycle, it's quite clear to then get to Fermat's theorem. Since any A is some n arrows, like 4 is 4 arrows, since if we start at 1 and follow 4 of these arrows, we get to 4.
Mm-hmm.
So if we then raise it to the 6th power, that's multiplying that number of arrows by 6, but any 6 arrows is just a full loop. So this is n loops, and n loops takes it back to where you started. It's just 1. So
Right.
anything to the 6th power is 1 mod 7 as a consequence of this cycle.
Mm-hmm.
And we'll get a similar cycle for any prime. But why do we have this p minus 1 cycle? So first fact we'll take is that the integers mod p are a field, which is to say that they have addition, multiplication, and inverses in both operations. So any number has an additive inverse and a multiplicative inverse. Except for 0.
Except for 0.
We can't.
Yeah.
Yeah, we can't divide by 0. So this means that if we take the non-zeros using multiplication, that's a group, since a group has some operation with inverses. So if we take multiplication as our operation, because it's a field, we will have multiplicative inverses, and so we can just consider multiplication, ignore addition, and we get a group. And one of the properties of a group is that any element of the group to the order of the group is just the identity. And so here, the order of the group, we have everything mod p except for 0. We're using non-zero. Is my cursor visible?
Yes.
Yes.
Okay. So we have all p except for 0, so that's p minus 1. So this directly gives us Fermat's little theorem.
Mm-hmm.
But it's not enough for a cycle. Like, this will hold even if we don't have a single cycle. So we need something a little stronger. We need some element g such that there's no smaller power that it gets to 1. So this g will be called a generator, since it generates the whole cycle. So g, because every element to the p minus 1 is 1, g will have that property, but there's no smaller power, so it must hit every element along the way, giving us a cycle. So this is what we're looking for, this generator. So if we consider just this equation, that means that the polynomial x to the p minus 1 has p minus 1 roots, because any of the elements to the p minus 1 is 1. So this will evaluate to 1, and then the whole polynomial will evaluate to 0. So every single element is a root of this polynomial. And one of the nice things about this being a field is that we have factorization. Fields allow for factorization. So if you consider the 6th case, where we're using the prime 7, so this is 7 minus 1, then we can factor this using all of those roots. But we could also factor this over the integers. So one of these roots is going to associate with this polynomial, that is the polynomial for the first root of unity. Another will be the second root of unity. Two of them associate with the third roots of unity. And then the final two with the sixth roots of unity. And this is the case that we care about, because the whole idea of the sixth roots of unity is that they generate a sixth cycle. So because two of these roots are associated with this polynomial, we will necessarily have a generator. So we get a p-1 cycle. And this works for the integers mod p, but it's not like we didn't use anything special about them. Oh, yes. This is the example from earlier. What are the generators here?
Multiplication by 3.
That is one of them. There's another generator.
The other one would be, I suppose, multiplication by 5. Multiplication by 5? No.
Yes. Yeah, it is.
Is that it?
It's the inverse of 3.
Right.
So multiplication by 5 is like following the arrows backwards.
Right.
Yeah, so those are the two generators here, but more generally, for any field, the non-zero multiplication will be a cycle of order the size of the field -1. So that applies with the integers, but it applies more broadly.
For any finite field, yeah.
Yeah, this is specific to finite fields. Since we're using the size of the field and then subtracting 1, it kind of doesn't make sense to do that unless it's finite. So we can apply this anywhere we get a field. So this is what we'll do with the integer polynomials. But the integer polynomials are infinite. They go infinite in the coefficient direction and the power direction, which means we need to do something about that. So we could perhaps apply mod 2 to get rid of all those coefficients, and then mod some polynomial to get rid of the infinite powers. So now we have only a finite amount. We can apply this. This will be a field.
Ooh.
So let's see what happens when we multiply by x. We get x, and then x squared, and then x cubed. But because the modulus is cubic, we can reduce this.
So that's negative x minus 1.
Yes. But this is also mod 2. So negative x minus 1 maybe would be better.
Well, x plus 1. It's just x plus 1, yeah.
Yes. These two combine, the 2 disappears,
Right.
and we just have x plus 1.
Yep.
So then what is the next step in the cycle?
So x squared plus x? Sorry.
Yeah.
Then
you get the
after
next
that, so what will this reduce to?
X squared plus x plus 1.
Yes. Those combine, that disappears. And then the following one.
X squared plus x plus...
X squared
x
plus
squared plus
1,
1,
right?
yeah.
Yes. So the x cubed and the x disappear, and then we get a 1. So now, once again, if we add the modulus, the x cubed and the x will disappear, and we just get the 1. So that completes the cycle. So we have this cycle. What is the order of the cycle?
7.
Yes. So that means that we have a generator to the 7th equals 1. Now from earlier we said that this power is the size of the field minus 1. So that implies that the field has order 8. And 8 is 2 to the 3rd. We get this 8 because we're using mod 2 and a cubic polynomial. So any polynomial with a power of 3 or higher can be reduced. So the only relevant coefficients are the linear the linear, the constant, and the quadratic. And then we're in mod 2, so there are only 2 options.
So
for
we're
each of
only
those.
missing
So we
the,
get 2 to the third.
just as the integer case, we're only missing the multiplicative identity. Or sorry, the additive identity, I mean.
Exactly. Yes. We
Okay,
must
cool.
remove that because it's it doesn't have an inverse.
Right.
So what this means is we could instead take like mod 3 and a cubic or a quadratic polynomial, and that would give us a field of order 9. So we'll have some generator of order 8. And this is what that cycle looks like.
Ooh.
X is not a generator. It just makes a 4 cycle, but we do have some generator. X plus 1 is a generator. Actually, I think a good question is how many generators are there?
In the general case or in this specific case?
In this specific case.
4?
Yeah, it would have to be the 4 like odd offset. Yeah, like the first element there, the second or the third element there, the fifth element and the seventh.
And then what about your other question? What about generally?
I don't know, because I think it looks to me like you're selecting the like the polynomial modulus in a kind of clever way here, where you're guaranteeing that.
Let's say we know the size of the cycle.
Well, if you know the size of the cycle, it's just the amount of coprime elements to that cycle, like.
Yes.
Yeah.
But you're right. I am specifically picking certain polynomials.
Yeah.
So
I'm wondering what's going to start happening if you don't do that.
In order to make this work, we need a field. And so that relies on both of these being prime.
Right.
If this is composite, we won't get a field because x times x is x squared, and so x won't have an inverse. And then also if we use 4, that's composite, so like 2x times 2x is 0, so 2x won't have an inverse. So there is that other case. So, okay, here, I'm going to pause for a bit. So we've covered everything with the fields and the primes. That's the nice case. That's kind of setting the stage. Now, as you said, you're wondering what happens if we don't. That is what we will look at next. I just wanted to pause to see if there's any questions at this point.
So we have this construction that works any mod p and then just any polynomial irreducible mod p. Is that what our restriction is?
Correct.
Okay.
So
and specifically,
yes,
we're concerned with the reducibility of that polynomial within the field in question. Is that right?
Yes.
Okay.
So that is why, like, I frame this as mod 2 before selecting the polynomial, because that polynomial is dependent.
Right. Whether it's factorizable depends on the integer modulus.
Yes. So we used x squared plus 1 in mod 3. This would not work mod 5 or mod 2.
How are you figuring that out off the top of your head?
Okay, so x plus 1 squared is x squared plus 2x plus 1.
Gotcha.
In mod 2, that doesn't work.
Right.
My thinking is if this goes to 0, then something squares to -1. And so like mod 5, 2 squares to 4, which if you add 1, that's 5.
Right. Okay. Yeah.
So this being prime really just depends on the prime value mod 4. So since 3 is 3 mod 4, this is prime. It would also work for 7 and 11, and but generally it's a lot harder to determine, especially when the polynomial has a higher degree.
Okay.
So we're going to go away from the polynomials and back to the integers. So we've seen that non-zero multiplication in the integers mod p forms a cycle. But this is not just with primes themselves. We also get non-p multiplication in the integers non-p multiplication in the integers mod a prime power forms a cycle. And so this, by non-p, I mean if we only use everything that is not a multiple of p. So this cycle kind of generalizes beyond just the primes, also to their powers. So an example of that in mod 9, we get this cycle of everything that is not a multiple of 3.
That's still just a special case of composite multiplication, though. Or sorry, coprime multiplication, though. I mean, is there something special that I'm missing here? Like, insofar as 2 is like multiplying by 2 is coprime to 9. Like, even if we pick something that is not a prime multiple, or sorry, a prime power, such as 6 as our modulus, then multiplying by a coprime number, you still get the same result. Maybe I'm just jumping ahead of you.
You will not always get a single cycle.
Oh, I see.
Like,
You're saying like we're worried about like having a cycle of 2 and a cycle of 3 that are disjoint from each other.
Yes.
Okay.
So 2 is a generator of everything mod 9.
Yeah.
Which is a fairly nice property, but in general, we don't always have a generator. You may need 2 or 3 or 4 or any number of generators.
Oh wait, did I maybe my example, maybe I misunderstood my own example. If 6, in the case of 6, if you multiply by
like mod 6 or
I was confusing myself between addition mod 6 and like this multiplication mod 6.
Multiplication mod 6 does give you a cycle, but there are other examples you could pick that will not be a single cycle. And I do have one prepared, so
Okay.
we will see that.
I'll shut up.
That will clarify. Oh, no, it's a very good point.
No.
Because I think it was important to add motivation for why we care about a cycle. And that becomes more valuable once you've seen when it's not a cycle.
I wait with bated breath.
Before we get to that, this is a 6 cycle, and that's because we start with the 9 integers, but a third of them are multiples of 3, so we subtract a third. So in general, this will be p to the n minus p to the n minus p, which we can rearrange to this form. And this is just the amount of numbers coprime to p. In general, the integers mod a prime power, if we're just concerned with multiplication, is a cycle of this size. And this is helpful to know because it allows us to evaluate any number. Like if we want to know multiplication mod 75, we can just break that into the prime powers, 3 and 25, which then gives us those cycles. So this is a case where we don't have a single cycle. But the caveat is this only works when p is not 2. So it only applies with odd primes. 2 is an edge case, as it often is, sadly. So with mod 16, 7 and 9 and 15 all square to 1. And something that squares to 1 means that it should be halfway around the cycle, but we can't have 3 different numbers all halfway around the cycle. Mm-hmm. So this can't be a single cycle. We end up with this structure of 2 cycles. So 9 is halfway around the first cycle, 7 is halfway around the second cycle, and then 15 is halfway around both. It's 9 times 7. So any number is kind of given by its product of each of the cycles. So like 9 is 9 in this cycle and 1 in this cycle. Kind of this sad edge case, but it does still have a pattern. Mod 2, we just get a 1 cycle, which is like trivial. It doesn't really mean anything. 4 is a 2 cycle, and then anything higher, we just get a single 2 cycle and then some other cycle. So the maximum is 2. It's not that bad, but it's not quite as nice as the odd primes. So now what this means is if we have 2 times k odd primes, we get k cycles. 4 times k odd primes gives us k plus 1 cycles because we have that additional cycle from the 4.
Mm-hmm.
And then any higher power is k plus 2. And then also, if there is no 2, we also just get k cycles. So 2 doesn't really do anything since it's a 1 cycle, and that can just be absorbed by anything.
Right.
So this is the integers. Now we might wonder, what about the polynomials? Is there a way that we can, given that we're in the polynomials mod a prime, if we have some polynomial, is there a formula for which we can get all of the cycles like this? And because primes work the same way in the polynomials, we can break any polynomial down into its prime powers. So what we really need to study is just the prime powers, and then that will give everything else. So when I first started thinking about this with the polynomials, I was very curious as to how the prime powers would act, and I didn't really have a good intuition for what they would do. I was kind of hoping that they would have cycles, but expecting that maybe there were some edge cases like 2 in the integers, so maybe the small polynomials act differently, but at some size there is some regularity. And so I wrote a program to kind of evaluate this. Can you still see? I switched things up, so I don't know if I shared my full
Yep.
screen.
Maybe just
We should
zoom in
be
a little
VS
bit,
Code
but
now.
I think you're good.
Okay, yeah, that's. How do I do that?
Control scroll up
You.
or no? Control plus possibly.
That's not working.
Try control plus. Oh yeah.
That is working. Okay, it should be good. Okay. So here we have p as 2. So we're in the polynomials mod 2. And then this is my polynomial. This is the example I gave earlier, x cubed plus x plus 1.
Okay.
So I'm going to run this just with its first power, and we get a 7 cycle. So we saw that earlier, because this is a field of order 8, it will have a 7 cycle. Now, if we try the second power, we get a 2 cycle times a 2 cycle times a 2 cycle times a 7 cycle. So already this has failed. We don't get single cycles with powers of prime polynomials. And then if we raise this a bit higher, let's see what happens. So each of these is another power of this polynomial. So we get 3, 4 cycles in a 7, and then 3, 2, 3, 4 in a 7. So because this is a cubic polynomial, mod 2, each time we raise it to another power, we're gaining 3 extra degrees. That's adding an order of 8 to the cycle. So we went up by 2 in each of these 3, and then we added 3 2s, and then went up by 2 in each of these 3, and then the 7 cycle always remains. But Yeah, there's always like these groups of 3.
So you're saying you don't know the general pattern here?
I do.
Oh, you do. Okay.
I didn't know the general pattern when I scheduled this, but I'm almost positive I figured it out last night.
Oh, okay.
Which was very exciting because my
Fresh
thought was
math.
I was going to go in this and be like, I don't really know, but I do. Before we get to that though, yeah, once we start to get to a higher power, this takes longer since we're like.
Just to make sure I'm understanding what you're actually doing here in your IDE.
Yeah.
Like, so you are just exponentiating that to the 7th power. Like your polynomial prime is that thing, and you're just raising that quote unquote prime to the 7th power, and we're just looking at the cycles of that group. Is that a correct recap? Okay.
So then we look at all of the polynomials, find their orders, and then if you have, because this is commutative, we can just count the orders of all of the polynomials, and if you have a count of the orders of a commutative group, then you can just immediately figure out what group it is.
Okay. Yep.
So now maybe let's try a smaller. Let's just try quadratic, and we can raise the power a little bit higher since it'll go faster. So now we start with a 3 cycle because this is a degree 2, mod 2, and then each time we're adding 4. And the pattern is kind of similar. We're getting,
I see. Yeah, you end up with
these groups of 2. So like
groups for each time.
Yeah.
Is this yeah? So
And
your program here is sorting the. Is that sorting the orders of the cycles there?
Yes. So it's sorting all of the powers of 2, and then the powers of 3, and then any.
Gotcha.
And then maybe let's look at a linear polynomial.
I'm starting to see the pattern. This is really interesting if true.
So here is linear. So what is the pattern that you're seeing?
I see a pattern. I don't know if I see the pattern. I see things that.
Any guesses? What is the patterns?
It sort of
looks like it's. Sorry, you go ahead.
Each new set of groups, they're all scaling up by powers of the whatever the scaling factor is, but each new group is following a slower progression. Is what it looks like.
Well,
a slower progression. What do you mean by that?
I think he's just saying that. Sorry.
This first one, it's going up. It's 2 once. It's 4 twice. It's 8 4 times. But then this second group is 2 for more times, and then it's going to be 4 for even more times. So it's going to be slightly slower every time. Maybe.
I'll start with the dumber and easier to check claims. You always have a 3. Or at least in that example, you always have. It's always increasing by 2 each time. It's increasing by 2 every other time.
Increasing by 4 each time. Increasing by 2.
I meant the amount of
cycles.
Yes. Sorry, what were you saying? It's increasing by 4 each time? Are you saying the sum?
The total order, if we multiply all of these together.
It's increasing, right? Oh yeah. Okay. I didn't notice that.
You're right. It is. We are adding.
Right.
That's kind of trivial since we're adding 4 times the amount of polynomials, so that must necessarily happen. But what you've noticed is less trivial, that we're adding 2 groups every time, and it is like I think I kind of understand the vibe of the slowness. Like
Yeah, I wouldn't be able to go into more detail without looking at way more examples.
Here
Yeah.
is the linear. So we're seeing the same thing every two, a single cycle is getting added.
Right.
But what's very interesting to me is if we view these together.
There's like a 2-4-2-4 pattern. Like there's a on the.
Are you saying these two outputs are related to each other?
They look like it.
This is the powers of a quadratic polynomial.
Yeah.
And then this is a linear polynomial.
So like on the second
And
one
actually,
there.
Let me run the other linear polynomial as well. So maybe first what we see is these are identical, since this is kind of a weird thing about polynomials, is that different primes can have the same kind of size. So x and x plus 1 are the same sized prime, so there's no real difference between them. They act identically, which is not a property of the integers. Every integer prime has its own size.
Right.
So, but
it looks like. Oh yeah, where did the other one
did
go?
that go away?
That disappeared.
Let me rerun it. Yeah.
But yeah, like, so are we saying that the like, it looked like it was just a direct copy of the linear one, just multiplied, where like each extra group was like, or each time you're adding instead of.
Oh
like,
yeah, I see that.
Like the first two elements in the linear one are like 2 and 4, not including the like the whatever that is, the first one where you're like,
this is just a 1 cycle.
Right, a 1 cycle. So then you have a 2-4, and then in the next one you have like your first two elements are like a 2-2 and a 4-4.
Yep. We have a 2 and a 4.
That seems to continue.
2 and a 2 and a 4 and a 4.
Right.
Then a 2 and a 2 and an 8 and an 8, where here is 2 and 8.
Right.
And if we bring back the cubic, or I'll do fewer.
So we know the pattern as soon as we can figure out the linear one. Is the claim, at least.
Yeah. So, which is really nice if that's true, because x is always a prime, and it's really easy to work mod x or mod the power of x.
Right.
Because you're just chopping things off.
Yep.
With another polynomial, you might like introduce some new lower ones, but and then this has just been 2, but if we change this to 3, let's do like 8. So this is the, I'm going to start this over. So we start with a 2 cycle. What just happened? Okay, we start with a 2 cycle, and then we're kind of adding these 3s, but we never get 27. So this is kind of, seems to be growing slower than the 2 case.
Oh, and also the
are you sure 7?
The add 1 or add 1 entry every two exponents is no longer following also.
Yes. But is there something that has replaced it?
I mean, it looks like it's like add 1, then don't add 1, then add 1, then add 1, then don't add 1, but I don't know if I have enough examples yet to say that with any confidence.
So in the 2 case, it was you skip adding 1 every second, and
right.
here
you're skipping every third.
And so we do see the same property. We always get that initial cycle from the field that is co-prime to our P. And then 3 corresponds to the 3, and then we have 3, 3, which is 4 3s, and then 3, 9, which is 2 3s and 2 9s. And as far as I can tell, we're kind of just copying things.
It does look like we're copying things.
And
Wait,
so now,
sorry, one more question about that. Maybe this is obvious for a reason that I'm not noticing, but is it necessarily always going to be the case that with one exponent higher, you're always going to include all of the same cycles that were in the former group? Could you go back to your examples there? Maybe it'll be your outprint, your printout there.
Like, okay, so like this will
Yeah,
always
like
be
that's a
subgroup
subset
of this.
of that.
Is what
yeah.
you're asking?
Yes.
It
appears to be holding.
I think so. Yeah, because if you
Oh wait, no, that one's not a subset of the next one. 3333 is
it
not
is
a subset of 339.
because a
Oh,
3 cycle is a subset
right.
of a 9
Yes,
cycle.
yes.
I think because the structure of this is embedded in this one. Like if we go back to the integer case, we could think about like this 6 cycle mod 9. Mod 3 we have a 2 cycle, which is contained here. We can just view it as the 1 and the 8 if we just reduce those mod 3, because we have 1 mod 3 and 2 mod 3. So you should be able to do something similar. Can't like explain why very specifically, but yeah, you should be able to just like consider everything. Like here we have everything considered mod 5th power or the 6th power, but if we just consider it mod the 2nd power, we should necessarily result in the same structure.
Okay.
So let me pull up the simplest example, which is mod 2 x, and get some more. This one I can go for the farthest because it's the simplest. And then I wrote this, which is like the formula that I believe to be the case. So the integer modulus is 2, the prime degree is 1, and then we only need to go up to 16. This, I did one fewer. Oh yeah, that's because it doesn't include the, okay. So these do match. In every case that I've tested matches.
Right.
So the answer maybe will become a little bit clear if I include the 17th power case. The 17th power, we lose 16 and we gain 32.
17 is 1 more than the power of 2. Is that where we're going?
Here we have half of the cycles are 2 cycles. A quarter of them are 4 cycles. An eighth of them are 8 cycles, and then we kind of have to fit in the remainder.
Okay. Why is that?
And so, yeah, I don't have, let me like go to a new slide. Oh yeah, that's one way to do that. So, let's consider this mod 2, and then let's see, and we'll use a power. Oh yeah, this would be a good example. Mod x to the 4. So this is going to give us these polynomials. So this is going to be, let's see, mod 2 to the 4th power, a 2 cycle and a 4 cycle. So maybe the question is, what is the order of each of these elements? So first, what is the order of x?
Mod 2, mod x to the 4th.
Oh, wait, this is, yes, this actually,
isn't it 2?
Will eventually go to 0. So we actually always need
the 1. Right.
So what is the order of this?
Please hold. So multiply it by, if you square that,
What
you
does it
get
equal if you square it?
x squared plus 1. From there you get
Yes.
x cubed plus x squared plus x plus 1. No, did I get that right? I think I got that right.
Yes.
Yeah.
But we don't really need to pay attention to the only possible orders are powers of 2 because the group has a power of 2, so we can just square this directly.
Yeah, it squares to x to the 4th plus 1, which is just 1.
Yes.
Mm.
So these arrows will be squares. So
Okay.
that squares to 1. So what is the order of x plus 1?
4.
Yes. And then this has order 2.
Mm-hmm.
Now let's maybe consider something else, x squared plus x plus 1. What does this square to?
X to the 4th drops out. You get... hold on.
Is it the same?
As
X
No.
cubed.
Wait.
You should get x cubed plus...
Yeah, I think it's
2x.
also x squared plus 1.
it is.
Oh, is it?
Let's, here is a bit of a, this will simplify everything. What is a plus b squared?
A squared plus 2b plus b squared.
But we're in mod 2.
Oh, sorry. Yeah, a squared plus b squared.
So, we really just, if we have any two things and we square their
Right.
sum, we just get their individual squares.
Right,
and
right,
this
right.
will, like, we can add a third one and a fourth one. So here we just kind of doubled the powers.
Yeah.
And then also doubled the powers, but the
Yeah,
4
the
dropped
left
away.
thing is the... Right. Yep.
So we're always just doubling the powers. So this is everything that's not cubic. If we now view something that is cubic, like what if we square x cubed plus 1?
That's also going to go to x squared plus 1.
It will
Right?
not.
X to the
We're
6th
going to
drops
double
out.
the powers.
So like you have x.
Oh,
that
right,
just goes
right, right.
To, that just goes straight to
Yeah.
1, right?
It does.
I don't know why I reduced the exponent. That was silly.
Mod x to the 4 plus 1, you were thinking of maybe.
Dropping
No,
the
I
d20.
just saw x to the 6th and dropped it to x squared. That was not correct.
Let's see, what's another? You would add an x in here. So what does this give us?
That should give you just x squared plus 1 again, I think.
Yep, another one of those. And then
X cubed plus
let's
x
see.
squared plus 1, I guess, is the next one. Which
Yep.
should just give you 1.
Yep.
X cubed
And then finally is all of them.
Right, yeah. And that should give the same thing that x squared plus x plus 1 gives, which is x squared plus 1.
Yes.
Like the cube terms are... all of the cube terms are always irrelevant if I'm...
Yes,
Yeah.
and the square terms.
Right, yeah, that too.
And so if we're in some mod x to the n, any term that is higher than half of it will be irrelevant when we square it.
Yep.
And then anything that's higher than a quarter of it will be irrelevant when we
you
raise
square
it to the
twice.
4th power.
Yep.
And so this is kind of the base intuition for why we get
I see.
half and then a quarter.
I see.
If we want to find the actual group structure of this, like, we could ask the question of how many elements have order at most 2.
So in this case, it would be 4?
Yes, these 4 have order at most 2.
Okay.
Cycles. Orders that have at most 2 will either be the start of the cycle or halfway around the cycle in this cycle, at the start or halfway in this cycle, at the start or halfway in this cycle. And so it's going to be 2 to the power of the number of cycles. And so since we have 4 of these, we must have 2 cycles.
We must have two cycles.
2
Or are you saying
of some cycle. 2 even cycles.
Wait, how do you arrive at that? If we have 4 of those elements and one of them is the multiplicative identity, that means that you have 3 distinct cycles, correct?
So if we're given some cycle structure and we want to count the number of elements that have order 1 or 2, that means it must have order 1 or 2 in this cycle and this cycle and this cycle and the rest.
Yeah.
So this has 64 elements of order 1 or 2 because there are 6 even cycles.
Okay.
And then this has 32, this has 16, this has 8, 4, and 2. So going the other way, if we know the number of elements that have order 1 or 2, we can then arrive at the number of even cycles. Because we know that this group has order power 2, we know that there can't be any odd cycles. We know that all cycles must be power of 2 because any subgroup divides the group. So this tells us that we must have 2 even cycles.
Okay.
And then that kind of trickles upwards. Like if we count the number of elements that have order at most 4, then that must be like for this cycle, it can be anything. This can be anything, but this, it can only be like one of the 4 sections of this cycle.
Right.
So we can then arrive at the structure from there. So in general, with this mod 2 case, what we really need to pay attention to is the smallest power of x that's not x to the 0. So here that's x to the 1. And so the first time it crosses 4 is its order. So this is order 4. But if we were instead mod x to the 5th, this would now have order 8 because order 4 no longer gets that x above the modulus. We need to square it again.
Okay,
so now
I see
maybe
where we're going.
let's work through finding, like let's work through this formula. I will use mod 11. So this is tedious. So I'm going to write out all of the different possible, what these numbers represent is the lowest power of a polynomial. Every polynomial must have the 0th power, otherwise it's divisible by x, which is the prime, and so it's not part of the multiplicative group. But these are the possible so in order for something to zero out mod 11 after squaring, let's say like order 2, anything with 6 or above, that works because this will go to the 12th power, this will go to the 14th, and those are all above 11, but none of these will. So that means that we have 5 cycles.
Right.
Now, for order 4,
you've got the 5, the 4, the 3 as well.
So that means that our
2's going to need a
3 cycles at least, 4.
Yeah, and then 2's going to be an order 5, an order 8. I mean, sorry, wait.
Yep.
Yeah, order 8.
So there will be 1 cycle with at least order 8. And then the 1 will go away after 16. And so we'll have 5 cycles that are all at least 2. 3 of those are at least 4. So that means that 2 of the 5 cycles are not at least 4. We'll have a 2. I should have just copied the 2. And then 3 of these are at least 4, but only 1 of them moves on. So we get 2 of them are 4 cycles. And then 1 of them is at least 8. And that same one is also at least 16. So this should be, the way in the code is the other way around. So 2, 4, 4, 16. So if we run this, we'll want to end 11 since this starts at 0. 2, 2, 4, 4, 16.
Nice.
Cool.
So this works in general for this x, power of x case mod 2. To generalize this, if we were instead to work mod 3, we now have the property that a plus b cubed equals a cubed plus b cubed because of Pascal's triangle, the binomial theorem.
Yeah. The second row, everything's mod 3 except for the 1 and the 1 on each side. Everything is 0 mod 3.
So
that's true for all primes, right?
Exactly. So the same idea applies.
I didn't know that.
Oh, I need it. Yeah. That's because if we think of like the choose function, if the prime, like aside from the 2 ends of Pascal's triangle, which are 1 and 1.
Yep.
If we have the prime choose a number that's less than the prime, then the numerator of the choose function will have that prime, but the denominator won't.
I see. So you get a multiple of the prime, and then it cancels out under modulus.
Yep. So we'll always be able to just distribute. This is a really nice property of mod p. We like using its own power can do this. So then like now instead of squaring things, we want to cube things.
Okay. So now we're gonna, I guess it would be the last please hold while I do the math. The last, like, what, 7 elements? Up to 1,
so
2,
what is
3?
The first element that is order 3?
I think it would be 4. Did I
Yeah.
get that right? Yeah.
And then order 9
Would be the
going to be over here.
yeah. The 3 and the 2 both, right?
Yeah.
And then 27 will grab the 1. So we should
Right.
have 7 cycles. 2 of them will be at least 9, and 1 of them will be a 27 cycle. So we'll have a 27, a 9, and then 5 3 cycles. And I don't know, this might be too large of a group to run this.
Wait, why is it a 27 cycle?
oh.
Why is the 1 a 27 cycle?
So this tells us that we must have 7 3 cycles,
Mm-hmm.
and that, or 7 cycles that have some power of 3.
Right.
This tells us that 2 of them also have a power at least 9.
Mm-hmm.
And then this tells us that 1 of those has a power at least 27. So we can kind of stack these.
Okay.
So like these are just 3, this is a 9, and then this is the 27.
I see.
So this did finish. We have a 27, a 9, 3s, and then
But like,
what I
is that?
left
What is
out
that
is
element
this
though?
2.
What is that 27 element? Do we know what? Do we know a generator of it? Or is that like a hard question?
X. I think.
Would X work? But like, if you multiply by X over and over again.
Oh, sorry, X plus 1.
Yeah, that makes more sense.
You want to see? We can work it out.
Okay, I mean, I'm down. Do you have a lot left after this? I don't want to sidetrack you.
No.
Okay, yeah, I would be down to work it out. Is X plus 1 always going to be a prime in every like modulus base?
That's a good question. Like a generator?
Yeah, is it always going to be a generator of the entire group?
Well, I mean, it's not a generator here, but I guess the question is it a generator of the largest cycle? And I think
Right. Yeah. Yes.
so.
And it's not a
I don't know
generator
how to-
because of the whole group because that cycle is always going to be less than the whole group's size anyway. So.
Yeah, there
Okay.
is no full generator.
Right. Okay.
But like, this is gonna get messy since it's mod 3, but like X plus 1.
X squared plus 2x plus 1.
Yeah. And then I kind of prefer using negatives mod 3.
Oh no.
That makes canceling
Wait, but
easier
this
sometimes.
we just get Pascal's triangle again, like by working this out, right?
Oh yeah. The third power will be x cubed.
X cubed plus 1.
Plus 1. So then
X to the fourth plus x cubed plus x plus 1. Yeah.
And then we'll get
X to the fifth plus 2x to the fourth plus x to the third plus x squared plus 2x to the x squared minus x under your notation minus x plus 1 if I'm not mistaken.
Yeah, I think so. So then we'll get an x to the sixth. This will cancel with the negative. This will what are you gonna say?
I was gonna say maybe we should go look at the third term and then like cube that twice instead of going 27 multiples of x plus 1.
Go every like.
Yeah, like skip by 3s.
Yeah, because it can't have. The order must be a multiple of 27. Kind of, not really, because yeah. So if we just
why
skip
kind
by
of not
threes,
really? Isn't that what we just concluded?
I was kind of ignoring this 2 cycle.
So it's
But
possibly a
if
yeah.
if something, oh wait, never mind. Because if something has a 1 as the constant, then
Mhm.
it won't be even. But if it's a 2 or a -1, then it will be even.
Why is that?
Because in order to get to 1, a -1 needs to square.
Right. Okay.
So
Yeah.
like if we,
Yep. Yeah. The
yeah.
the one's term is always going to flip sign.
So that process that we did, this thing,
Yep.
is giving us the structure if we ignore the initial field
Okay. Yeah.
of order 2.
That makes sense.
So like we're since this is mod power of x, we're kind of ignoring mod x, which ends up just being the field mod 3, which is like that integer case of the Fermat's little theorem. So we're splitting the problem into what is the constant term. That gives us
I see.
some
Yeah.
order that's not a multiple of 3, and then what is the smallest non-constant term. That power determines the order as a multiple of 3.
Right.
So this to the third power will be x cubed plus 1, and then to the ninth power will be x to the ninth plus 1, and then x to the 27 plus 1, which that cancels out. I mean, that's a less satisfying way to see it.
Yeah. Yeah. No, but that makes sense though.
Yeah. We could skip ahead. So like this 18 is going to be x to the 18 minus x to the 9 plus 1. And 6 is going to be x to the 6 minus x cubed plus 1.
Mm-hmm.
So then 24 is going to be the product of these. So we're going to get one of these and then
Shifted
multiply
by
9. So that's going to be,
x to the 9th.
but they're going to negate
x to the 12. Yeah. That one's x to the 12. That one's x to the 15, but there's a minus on it. Yeah.
and we get
X to the 24th minus. Yeah. Okay.
That's 24. And then this was squared. So that would give us like,
Ooh.
we have a positive, negative, positive, negative, positive, negative, positive, negative, positive. So then when we multiply by this, it's going to give us x to the 27 plus 1, and then this cancels out.
Axiomatic System in the chat just posted how this is a Sierpinski triangle that we are drawing in text.
Oh, okay.
So like that, you see how like every third term you get like a skip of 2 powers. I don't know. I would say just look at the chat. It'll probably make more sense.
Okay. This one.
Like, so the red things are the 2s.
Yeah. Okay.
Like the first term is the 1. The second term is like x plus 1. The third term is like x squared minus x plus 1. That makes sense though.
And so because of the repetition of the Sierpinski triangle,
right. Yeah.
That cancellation. Yeah, so this generates a 27 cycle.
Yep.
And then anything else with a constant term will also. The only thing that remains is then that question of like what about when we did that thing of going to a quadratic polynomial? Then we got like the doubling behavior.
Yeah.
Why does that happen?
Why does that happen? I don't know.
So this, if we, let's say we have this is a prime, and we're going to consider its square. So by the property that we saw earlier, this is x to the 4 plus x squared plus 1.
Yep.
Maybe, okay, let's find the order of some elements. So like x squares 2. Forgot that
What was
button makes a
that?
clock. That's my clock button. I accidentally pressed the clock button. That squares to x squared, which then squares to x to the 4th. That will just turn into x squared plus 1. And then that squares to x to the 4th plus 1. Wait a second.
That's
Squares to... Oh, wait a second. What happened?
Oh yeah, that's not right. Yeah, wait. Yes, it is. Wait, I'm confused. What's wrong?
But that would then go back here. That goes back.
X squared plus 1 squared gives you...
Oh, right.
The ones term doesn't vanish. Or does it? Wait.
I messed this up. There's something about this case where we can't just square them. Let's just look at the powers then. So that goes to... I need to stop pressing.
I want you to give another talk about how this slide making tool works, because this is sick as hell.
Okay, yeah, I can do that.
Hell yeah.
Let's see. That goes to x squared plus 1. Which then so now these are not squaring, they're multiplying by x.
Yeah.
So we go to x cubed plus x, and then that goes to x to the 4th plus x squared, which is 1. So
X to the 4th plus x squared. Yeah. Yep. Yeah, I agree.
Since it cancels with the mod. So this actually makes a 6 cycle. X generates 6 cycle because this is a quadratic polynomial.
Mm-hmm.
So its initial field, when we just use a single power, is a field of order 4, since we're quadratic 2. So we subtract 1 and get 3. So we'll always have some kind of 3-ness in the group. So this is a generator of the 3 cycle. But we want to kind of pay attention to what happens outside of the 3 cycle. So this is the element that has order 2.
Order 2, yep.
No, wait.
No, x cubed. X cubed is, yeah.
Yes. X cubed has order 2. And the other elements that have order 2... Let's see. I believe x squared plus x plus 1.
Wait, sorry, mechanically, how does x... You're saying if I square x cubed under that modulus, you just get 1. Oh, yeah. Sorry, yep. No, you don't get 1. Squaring x cubed, you get x squared plus 1.
You get x to the 6th. Yeah, go ahead.
Yeah, and then x to the 6th minus 1 is the modulus times x squared minus 1.
Oh, shoot. Okay, yeah.
So this ends up just being 1. X to the 6th is 1.
Mm-hmm. Okay.
So then this squares to 6th, 4, 2, 1. But then a multiple of this is 6, 4, 2. So it also goes to 1.
Right.
And then what is the other one? Oh, yeah, it is x squared plus x. Since that
square
squares
that,
to
you get
x,
x to the 4th plus x
to the
squared.
4th. So then with the modulus, that cancels.
Yep. Yeah.
And so basically what we're doing when we square these, we're doubling the powers, and then we're kind of reducing using this squared modulus.
Yeah.
But if we think of that in the other direction, if we don't need to double the powers because this already has doubled powers. So we can half these powers and just use the modulus itself. So
But that only works in mod 2, right?
Yes. In the other ones, we would be concerned with cubing.
Right.
And
Right. Yep.
yeah. So the reason that these have order 2 is because if they're equivalent to 1 mod the prime itself.
Yeah.
So we can just cancel this, and then here.
And that is Fermat's little theorem. Like you are raising some polynomial prime to a power, getting a prime power, and the power that you exponentiated it to.
Well, the theorem kind of breaks when we raise the prime to a power because we no longer have the field. This is kind of everything that's going on outside of Fermat's little theorem.
Okay, yeah, never mind.
Like if we wanted to view, for example, x cubed plus x plus 1, where does this square to? We would get 6.
Yeah, x to the 6th plus just x squared plus 1. But then subtracting off the x to the 6th, you would get shoot, I'm not sure. Wait a minute.
Is it
trying to do this in my head? Yeah, go for it.
Is it x squared?
It is x squared.
How'd you get
that? Just the way you did, but x to the 6th becomes 1, so we have 1
right.
plus x squared plus
yep.
1.
Yeah. Thank you.
Instead of squaring this and reducing it by the square of the modulus, we could also just do the other order if we just use the prime itself, where x cubed equals 1. So x cubed and 1 go away, and then we square the x.
Right.
So anything that reduces to x mod the prime
it reduces
will give
to x
us
squared and the prime squared.
So also x squared plus 1. If we add the prime itself, the x squared and the 1 cancel, and we just get the x, and then that squares to x squared. So, and we can check if this squares, we get power of 4 and 0. That will cancel to give us x squared. So we can kind of do this in either order. And so to get the orders, of these, this process just reduces it down to that initial field, like the order 3 field. But we know we're always, or the order 3 group. So we know we're always going to have that order 3 group. What we're really concerned with is the group outside of that. So we
Right.
don't really want to pay attention to these. We just want everything that's equivalent to 1 mod the prime.
Right.
So if we were instead to use a higher power of this, then squaring this, we would only be able to cancel up to a certain point. Like this would give us x to the 16. No, that's not. Yeah, plus x to the 8th. So these would no
Where are
longer.
you getting a degree 16?
We're
If
raising it to the
we take this to the 4th.
Oh, but that should be x to the 8th.
That's
That should
Oh
be
yeah,
x to the
sorry,
8th
you're
plus
right.
x to the 4th plus 1.
Let me switch this to 8 then.
Okay.
I was thinking of the other way around. Thank you. This no longer squares to 1. Because, like, when we square it, the powers are not high enough to use this 16. So we need to raise it to the 8th power in order to get this 16, in order for it to cancel out. So this is very much the same exact idea that we had when we just used x. Like, we're concerned with smallest power and then like how many times we need to square it in order to get above that threshold. It's just anything that. Go ahead.
now it's powers of the polynomial base instead of just x, right?
Yes.
Okay.
And so the same idea will apply. It's just that now we have like twice as many copies of everything because this is a second power polynomial. So like when we were using the second power, everything squared to 1.
Right.
But as that goes up and up and up, it's no longer the case. And so we can think of applying something similar for any prime polynomial that we put in. The only thing that really matters is its degree.
Yeah.
And then we can kind of just think of it as being x and viewing everything else as how high it needs to get to pass that threshold, and then just having a multiplication factor. And that is why we get this kind of
Cool.
doubling. I don't know if that fully makes sense.
Yeah, it's a lot to
but
hold in mental RAM all at once, but I think I follow at
yeah.
least the individual steps there.
Yeah, I haven't fully like written out a concrete proof because of that, but like I'm like the idea generally makes sense that I believe why this is happening.
Is this going to be a GrayCuber video?
I don't know.
Why not?
It's a lot. It's
Oh, I guess so.
Yeah.
That's a forcing function for you to boil it down to a simple proof.
It is. I might at some point, but right now I'm like my main focus is like entertainment. I know
Gotcha.
that doing something this complex will limit viewership.
Sure, yeah.
So it's I love this problem. I guess what I'm really thinking is just like I couldn't do this every video.
Sure, yeah.
But I'd like to do it at some point. I just need to figure out a way to. This was helpful in like figuring out how to simplify it by seeing what questions people had.
Mhm.
But yeah, everything like first half is fairly straightforward, but then as soon as we got to like this
Right.
part, it's yeah, I'm still confused by it.
So is this
I
a
don't know
question
how
that
to...
I mean, is this a question that you are aware of people having asked before?
I have no idea.
Okay.
I just stumbled upon it because I just wanted to look at all of the... I started by just asking the question. I was curious of like, what do rings look like if we mod by a prime and then mod by any polynomial?
Yep.
And so then I started just working out small cases, and then I noticed, oh, there's a pattern. Like whenever we combine two prime polynomials, their groups multiply, and I was like, oh yeah, that makes sense because when they're primes, so they're kind of going to act differently. And so then I started studying the prime powers and got to this.
Jakob says in the chat, is it too late to ask what the pattern was? And the answer is, I think you're looking at it, or at least for a few cases of small.
What the pattern of?
I think
Like
he meant what the
what
pattern.
the answer of the pattern, or what the like question of the pattern?
I don't know. I won't speak on his
Basically, an overview of what he missed because he just got here.
I think he missed everything.
Okay.
Yeah.
So...
All right. Let's hear the talk again in like 3 minutes.
Let me see if I can. If this makes sense, if we're taking like, or actually, this should be a...
No worries. You're good.
I
You're
don't...
good. No need to be sorry.
I don't have...
It's recorded, so if you want to watch on YouTube, you can.
I think this would be a good... let me attempt a summary. If this notation makes sense, we're taking the polynomials of a finite field, and then we're factoring out some power of a prime polynomial in that field. This Q is prime in the field. And we're asking what is the group, or yeah, that shouldn't be a 2. Just any power. Like how does that behave? Because in the integers, if we start with just the integers and take full cycle, as long as the prime isn't 2. So I was wondering if the same thing would apply here if we get a cycle, but we don't. The simplest case is this is the field of order 2. We're using 0 plus x as the polynomial, and we're going to take a bunch of powers of it. So first we get a 1 cycle, then a 2 cycle, then a 4 cycle, and then the product of a 2 and a 4, and then a 2 and an 8, and a 2 and a 2 and an 8, and so forth. And the general idea is half of them are a 2 cycle, a quarter of them are a 4 cycle, an eighth of them are an 8th cycle, and so forth, with some like squeezing as we need. Like here, there is no 4th of 6, but it's like using floor functions or ceiling functions. And then if we, instead of a linear, use like a quadratic prime, and we just take the linear pattern. Well, we have instead of starting with a 1 cycle, we start with a 3 cycle. And then instead of having a 2, we get 2 copies of a 2. And then instead of having a 4, we get 4 copies of a 4, or 2 copies of a 4. Yeah. And so this has 2 copies of a 2, 2 copies of a 2, 2 copies of an 8, which corresponds to 2, 2, 8. And so then if we did like a degree 3, then we would get 3 copies of each. So there are 2 copies here, 3 copies, 2 copies, 3 copies, and so forth.
He says, what permutation did you say this was again that's decomposing this way? I'm not sure I understand the question. What permutation do you?
Group? Which group? Like if
Oh, the. Yeah, I'm not sure.
Yeah.
Yeah, that's this like in the console there. In case it wasn't clear, that's the cycle decomposition of the
yes.
group.
So if we just use the units, and all of the yes. Yep. Yeah.
Sweet.
We
Thank
can
you.
just evaluate the X case and then yeah. Oh,
That was beautiful. The slides were beautiful. as
Thank
always.
I'm so pleased that I was able to solve that last night.
Yeah.
Yeah, that's great.
That's a lot more satisfying than coming to the talk and being
Right.
like, I don't really know.
Write a paper.
Which is what I was expecting.
Although I want my name on it. Just kidding.
I thought of writing a paper sounds awful, but maybe at some point.
Cool. Sweet. Any other questions?
I think I'm pretty good.
Awesome.
Well,
Dearab asks how. Dearab asked in the
Oh,
chat,
yeah.
how sure are you that this isn't known?
Like 0.1%. It is certainly possible that someone has looked at this before. I can't think of a reason why no one would have. I haven't really done any attempts. I just didn't want to look it up until I solved it, and I solved it last night, so there hasn't been a lot of time for me to further research.
Cool.
So, yeah, I'm pretty sure that this is known. I just don't know by who or when.
Cool.
Like it
wasn't known by me.
Look that up.
So I
Yeah, exactly.
Yeah, It's like in general is modulus of polynomials is. I'm assuming modulus of polynomials is studied, but modulus of a prime of a polynomial. Like, do you know it? Do you know of people who study that or no? Because if that's a thing, I don't know about it.
Or even just like modulo powers of polynomials. I haven't really seen that come up at all.
I feel like I've seen that somewhere.
Maybe, but I mean, not very often when people talk about polynomial rings or whatever.
Right.
So, yeah, and now that I can sort of talk, so TheGrayCuber kind of said this more or less, but just to be clear, to swap like finite fields, like this is how you get the finite field. You do like this thing.
Right.
You just take the irreducible polynomial.
Mm-hmm.
So, and like modulo a polynomial and a prime is such a common operation, like that's built into like that's one of the built-ins in Mathematica because doing it. Someone was doing, not me, but someone. Yeah, and so, but like I've never looked at, like it's not like I knew the answer beforehand.
Gotcha.
Now I'm wondering what would happen if we use
TheGrayCuber, just an investigation.
Like any finite field polynomials rather than just the primes. I may have to.
What do you mean by any finite field rather than just the primes?
Like if we use the field of order 4 as the coefficients for polynomials and do the same thing.
Instead of integers
But
modulo,
like,
whatever.
Okay, so that's like the same thing as modulo, like polynomials, one of which is irreducible, I guess? Like the field of order 8 is polynomial ring mod 2 modulo a cubic. And so if those are the coefficients, then you have those, and like also, yeah, as you were saying, like another variable y.
So that is outside of what I looked at, so it would be interesting to see that as well. I'm not really. I would
base-
guess based on this that the smallest polynomial case goes upwards, but I don't know how the smallest case would work.
So we're talking like a polynomial in two variables where one variable generates the base field and the other field is the polynomials that we looked at, right?
Yeah.
Okay.
Yeah.
And to review the parts couldn't pay full attention to, see if I can find like a reference for someone doing something similar.
Yeah, if you find something, post it in the chat. Cool. Thank you a lot.
Yeah, I don't have anything
appreciate
else to add, so
Yeah,
thank
was
you
excellent.
everyone for
I appreciate
the
it.
talk. We'll
You've made me want
see you
to
next
write
time.
my own like graph decomposition tool. So
Ooh,
maybe
yeah.
maybe I'll try that tonight. Maybe that'll be my little weekend project.
Be fun.
Yeah. All right. Thanks a bunch. I'll see you guys.
Right,
I'm gonna
thank
drop
you.
off.
Bye.